Yesterday we talked about independent events. And if we have the probability of independent events, we talked about how you just multiply the probabilities, right? That was the first part of the notes yesterday. Let's turn the page. Then, yesterday, we also talked about probabilities of events happening at least once, how that's actually really complicated a lot of times to figure out. So it's easier to look at the opposite probability and then subtract it from 1. Okay? So remember this. This is going to be important. And just quickly read through example 4. Okay, let's start going through this. So, 20% of adults smoke. All right. That means if we're looking for the probability that out of 10 adults that at least one smokes, that there are many ways for that to occur, right? So if you imagine each person having a number, like 1 through 10, at least one person smoking could be person 1 maybe smoking, or number 2, or number 3, or number 4, all the way down to number 10, all right? Or it could also be a couple of them, or 3 of them, or 4 of them. Like, all those are possibilities, right? That is way too complicated to figure out. So the easiest thing to do, what's the opposite of at least one of them smoking? None of them smoking. So we're going to do 1 minus the probability that 0 adults smoke, which is going to be the same as this. If we're looking at each adult individually, we want to find the probability that the first one does not smoke, and the second one does not smoke, and the third one does not smoke, and so on and so forth. Okay? But what's the probability of not smoking? %, so that's 0.8 times 0.8, and so on until we have 10 of these. Does that make sense? Because each one has an 80% chance of not smoking. So what's an easy way of writing this? We don't have to type it all in. 0.8 to the 10th. And so now we can finish the problem. The probability that at least one person smokes out of a group of 10 is the same as 1 minus the probability that no one smokes, which is the same as 1 minus 0.8 to the 10. Excuse me. And then we just type that in. So what is that going to be? What is it? Should be much higher than that. Did you forget to do 1 minus that? .89, 0.90. If we round to 2 decimals, which one is it? 0.90. Okay. It should be 0.89 if we round to 2 decimals.
Looks like it.
What's
89.26?
Johnny?
Oh, wait, yeah.
Only if it's a 5 or higher, right? 0.895. Okay. Alrighty. Anyway, so that's another at least problem making life easy. Okay, so that's kind of where we left off yesterday. Next, we're going to talk about dependent events, which is really, as far as calculating the probabilities, isn't much different than what we did just now with the multiplying. It's just that instead of having 0.8 all the way through, the probabilities might change from event to event. Okay, because as we saw yesterday, if one thing affects the other, then the probabilities are going to change. Okay, so go ahead and read example A, or 5, and answer parts A and B real quick.
I know, I forgot to. It's like, it runs out of battery just like twice a month. Okay, do you have the Android charger? The Android charger works for that? Yeah. That's so weird. My calculator. I have Androids or calculators.
There it goes. All right. All right, let's talk about this one. So what is the probability of picking a black car from this?
25%.
Okay, I hear lots of correct answers. Let's start from the beginning. It was originally 400 out of 2,000, which is the same as 1/5, which is the same as, if you want to do percent, 20%. Okay? I like writing out the original one because it'll help with part B. What is the probability of picking a black car once we've already removed that black car the first time out? Well, now how many black cars are left? And how many cars total? Okay? And I don't think that reduces. So I know that this is 0.2. What is this approximately? 0.1995, and so it's really close, right? Pretty reasonably close. Example 6 is similar. Let's just do that one real quick. So let's say we have 20 cars to start. 4 are black. What's the probability of picking a black car? It is the same. It'll be 4 out of 20, which is 1/5. But now, what happens if I remove that black car I just picked, and we want to pick another one? What's the probability? Instead of 4, there are 3 and 19. And what is that approximately? So about 0.16. Okay, so here's all you need to really understand from this. When we're looking at something with a lot of population, in this case, a lot of cars, right? Removing one from the sample, it does affect the probability, but not by much. Okay? When the sample size is smaller, you can see that the drop is much more significant. From 0.2 to 0.16, that's a lot more than 0.1995. Okay? So that's really all they want you to do when you're comparing. So you need to remember, if it's a big sample size, probabilities will be pretty similar, but if it's a smaller one, then they are going to change more drastically. Okay? Let's go on to the next page. Okay? So for dependent events, We kind of defined this in class yesterday, but let's write it down again. These are two events such that the probability is affected by the other events. So the probability of A would change if something has happened already, or vice versa. Probability of B is going to be different because A already happened. Okay? Let's do example 7 together now. Okay? Again, 20 cars, 4 are black, 16 are something else. If I randomly select 2 cars, what is the probability that they are both black? This is the same as the probability that the first car is black and the second car is black. We have the word and connecting these two events. So what are we going to do? What do we do? Multiply, right. So this will be, what's the probability that the first one is black? 4 out of 20 times, now that that one's out of the mix, what's the probability that the second one is black? 3 out of 19. And so that's, someone help me out. What does that reduce to? 3 over 95. Thank you. Okay. So, any questions on that? The last thing we got to talk about is conditional probability. And the symbol for that is you got two events kind of smushed together, but the way you read this is the probability of B, and this little symbol, that line, means given that A has already happened. Okay? So, the probability that B is the probability of B, given that A has already happened, is similar to what we did up here. Okay? For example, we could rewrite this exact calculation that we did up here, the probability of the first one being a black car and the second one being a black car, could be written as the probability that the first one is black, which is 4 out of 20. And then right here, when I said the second is black, really what we're doing is we're finding the probability that the second is black, but we're assuming that the first one we chose was black. Does that make sense? So that's a different way of writing it. You don't need to do it that way, but it's good to know that that's what that means. Okay? What you need to be able to do is look at probabilities like this and figure them out. So let's start with this one. What's the probability, again, 20 cars, same problem, that it's black, just one car? What is it? 4 out of 20, which is 1/5. Okay, so that's easy. What's the probability that the second car that I pick is black, given that I've already chosen a black car and gotten it out of there? 3 out of 19. Good. Everybody following that? Okay. What's the probability that I pick a second car that's black, given that the first one I chose actually was not black? 4 to 19. Very good. You guys see how to interpret that little line? Okay. Multiplication rule for dependent events. We've kind of already talked about it, but here it is if you want to highlight it. But all it is essentially when you see the word and, you multiply. Okay? You multiply the probabilities together, and if things are a little bit more involved, then they might look something like this, where the probabilities change as you multiply. Okay? If it's independent, then they're not going to change. They're just going to stay the same each time. Okay? Read example 9 and try A and B. You guys try it already? Okay. It's confusing? Okay, so think about it like this. How many items are we buying? 2. And we want to find the probability that we are really unlucky and both items are defective, right? This is the same as the probability that the first item is defective and the second item is defective, which is the same as the probability that the first is defective. What does and mean? Times the probability that the second is defective. And look, I don't care that whether you use this complicated notation with the given. You don't need it, okay? I think this will make sense just fine. What's the probability then that the first item I buy is defective? 3 out of 15. Now, we're buying 2 items. I'm not returning the item and putting it back in the mix and then potentially buying it again, right? So when I buy the second item, how many defective items remain? 2, and there's 14 total.
Why is it 14?
Because
you already bought one. Oh, you take it. Oh, okay.
Does that make sense?
Yeah.
So what is that going to be? Which is what fraction? Thank you. 1 over 35. All right. All right, so for part C, I wanted to do this one together with you guys because this is actually going to remind me to talk about the birthday problem again after I'm done recording. But so, oh, we didn't do B. Thank you. Is that what you said? Okay. Both are good. You guys tell me now. Can we just multiply the 2? What should it be? Perfect. Thank you. Make sense? Any questions on B? Okay. So let's just talk about this for a second. We're buying 2 items. And now we're asked, what's the probability that at least one is defective? That could happen more than one way, right? I could have the first item be defective, but the second one be good, right? Or, what else? Both of them be defective, that would be another option. What's the third one? First one's fine, second one isn't. Does that make sense? So there's 3 different things that would encompass at least one here. Does that make sense? Let's actually set it up and see how it works. And then I think you'll be pleasantly surprised when we do it the other way. Okay? So, probability that at least one is defective is the same as the probability. I'm just going to use D for defective and G for good, if that's okay, so we don't have to keep writing out all the words. It would be probability of D. Oh no. Okay. Probability of D for defective and second one good. Plus probability that the first one's good and the second one's defective, plus probability that they're both defective. And I kind of skipped a step, but when we were talking through this, I used the word or to connect the three scenarios. That's why we're adding the three scenarios up. Does that make sense? Because I said first one is defective, second one's good, or first one's good, second one's defective, or both defective. Those are the three things that would be at least one is defective. Does that make sense? What word, and I know I didn't write it, but what word is connecting each one of these? So we're going to multiply two little fractions here, two little fractions there, two little fractions there, and then add them up. That's what this is telling us to do. So let's do that. This first scenario, I forget about everything else and just repeat it. So if the first item is defective, what's the probability for that? 3 out of 15? And what's the probability then that the second item will be good? 12 out of 14. Very good. You guys see where we're getting those numbers from? Well, why don't you ask?
I don't know where to start asking.
We'll talk later. Plus. And now again, ignore all the other scenarios. Let's just set this one up. What's the probability that the first item is good? 12 out of 15. And what's the probability that the second one is defective then? Good. Plus, and now for the last scenario, again, you focus on just this last one. Buying two items, both are defective. What's the probability that the first one's defective? And once that one's purchased, what's the probability? 2 out of 14. Okay. And now just type that in real quick. You don't have to do it by hand. Just type it in the calculator. What are we going to get? 13 over 35. Okay. That is correct.
So, for this one that we did, you did the first one and then you did the second one. So then you're basically just mixing those two together, and if you're adding them together, plus, we didn't do the G and G, right?
No, because we didn't want that. The probability was for at least one being defective, so both of them being good wouldn't be one of those outcomes that we're interested in.
Okay.
Does that make sense?
Yeah.
Okay. All right, so check this out. Yesterday we talked about the words at least and how a lot of times finding the opposite probability and subtracting from 1 is a lot easier, right? You guys remember doing that? So, at least, I'm going to skip example 10 and just do it the second way, second option. The probability that at least one is defective is the same as 1 minus the probability of the opposite being true. So what's the opposite of at least one being defective? None of them are defective. Let's actually write that if it's okay with you. Both are good. That's the same thing, right? Well, we already have this one. We figured this out already. Which part did I find probability of both items being good? Part B, what is it? What's 1 minus 22 out of 35? 13. out of 35. So we could have done it in about 1/5 of the time. Because I want you to see, usually when I show that example, people are now going to start thinking, at least one, I'm going to try doing it the easy way. Okay? Does that make sense?
Yeah.
It was already calculated.
Yeah, both are good.
Both are good. We did it above. It was 22 out of 35. Now, had we not have done that, you would have just done 1 minus the probability that the first one is good, which is 12 out of 15, and then the second one being good would have been 11 out of 14. And then you still get the same answer. Okay? All right, let's turn the page. We're going to do one more example. So in this section, you guys, conditional probabilities, there's really not too much to worry about because most of the time you're going to be given like a table just like this one. And my approach for you guys is going to try to make just things a lot easier than they are. For example, there's lots of formulas that you can use for conditional probabilities, but for the stuff that you guys are going to do, the answers will be right in front of you. So let's just try doing it and see how we do just by looking at the table. Okay? So first one, we have, just so everybody understands, 478 total students, 227 male, 251 female, and then they were split up into categories: good grades, popular, good at sports. You have all the breakdowns there. Okay? And this is like their goal. Like, what is their primary goal? Good grades, being popular, or good at sports.
Which
Nope.
one's the good grades is the highest goal, or no, it's safe? Oh, okay, you just meant like that's one of the goals.
Yes. Yes. All right, so let's look at part A. What is the probability that one of these students out of the 478 has a goal of popularity? How many students are there that have that goal? 141 out of what total? Perfect. Okay, you guys pay attention. This is going to go quick, and then if you're not listening, you're going to be clueless. What is the probability that one of these students is male and has a goal of popularity? Good. What is the probability that one of these students has a goal of popularity given that they're male? So now, this last section right here, given that they are male, means that we're solely focusing on just the male row. Does that make sense? So what is our new total? Exactly. Does that make sense? And we're doing this without formulas, okay? I think it's a lot easier just to kind of think about it, look at the table, okay? Let's see if we can do this one. What is the probability that one of these students has a goal of popularity given that they're female? 91 out of 251. Perfect. And just so we can answer the next question, let's get approximations for C and D. What is 50 out of 227, roughly? So about 0.22. And what's the second one? 0.36. Okay. So I wanted you to see that because now we can answer part E. Does it look like the probability of having a goal of popularity might be influenced by gender? Well, according to this, it looks like girls tend to have that goal more than boys do on this chart, which may or may not be real. So I don't want anyone thinking, well, that's not my goal. But just on this particular problem. Does that make sense? Okay. Last one. What is the probability that one of these students is female given that they have a goal of popularity? So how many total are we zooming in or focusing on?
141.
Exactly, because we're just focusing on the popularity column. And now how many of those are female? And that's it. Does that make sense to you guys?
have to use those other formulas, like, it's just easier for you like this.
When they get, that's what I'm saying. When they give you a chart, absolutely, just look at the chart.
Okay.
You'll have a problem for sure like this, yes, but not the whole thing.
Should we simplify the ones we can simplify?
Yes. All right. So anyway, let's talk